Okay, having no questions, we'll go ahead and look at the next step in all this process, which is weak acids and bases in equilibria. We said that when we introduced the concept of pH combined with discussion of strong acids and bases, we could predict the concentration of the hydrogen or the hydroxide ion from the concentration of the acid or base. In most cases, when they were monoprotic acids, we just said they ionize completely. The hydrogen ion concentration is the same as the acid concentration. When it was something like a diprotic base, like calcium hydroxide or barium hydroxide, then we would have to multiply the base concentration times 2 in order to get the concentration of the hydroxide ion. But it's different in weak acids and weak bases. Weak acids and bases, by definition, are things that are not completely ionized. They are partially ionized or partially dissociated. So the way that we know this is strong bases contain the hydroxide ion. Whether they're very soluble or only sparingly soluble, they're still a strong base if they contain hydroxide. So weak bases react with water to produce hydroxide. But the hydroxide actually comes from the water, not from the compound that's basic. And with weak acids, they contain a hydrogen ion, but they don't dissociate completely. They only dissociate a little bit. So we can think of these introducing this definition and combining it with the equilibrium. We talked before about K sub C, and K sub C was based on concentrations for equilibrium. We introduced K sub P. That was based on pressures for equilibrium. So now we're going to introduce Ka, and that's called the acid ionization constant. So we'll consider a generic weak acid, HA, a generic monoprotic, it only has one proton, and it produces A- anions. So we can think of this, that HA, our weak acid, is in equilibrium with H plus or A-. Now, in an aqueous solution, you have water hanging around, so we can also think of HA plus water makes the hydronium ion. And remember we said before that the hydronium ion is actually a better representation of what exists in solution. Because we have water, has 2 lone pair, and we have this loose hydrogen ion. It's kind of hanging out. I have no electrons. Hey, baby, we got some. So you make this weird thing, the H3O plus. This lone pair makes a coordinate covalent bond. It donates both electrons, and we make this, and this is called the hydronium ion. So we can write H plus, which is what I usually do, or we can write H3O plus, which is what you see in the textbook. You'll usually just see me write it as H plus when it's a weak acid. So now we have this weak acid ionization, and we call the equilibrium constant Ka now because it's an acid. So Ka is equal to the hydrogen ion concentration times the anion A-, that's the generic, concentration divided by HA. Or we could write it, if you like to get fancy, as the hydronium ion concentration times the anion concentration divided by HA. So this is what you'll see me write most of the time. So now, if we're talking about a strong acid, it doesn't make sense to think about this because we say they're completely ionized, so the product concentration would be huge, like 100%, and it'd be almost nothing, like a 0, and you'd have an undefined thing. So they're very large, near infinity, but really sort of undefined, so we don't discuss them. The Ka values for weak acids are very small. And so we think of these as equilibria with small values. Is something wrong with the packet? Oh, okay. I thought maybe my pages didn't line up with yours the way you were looking at your page. So we can consider Ka, and then we can calculate pKa. Remember, we previously defined P as a function. pH is the negative log of the hydrogen ion concentration. pOH is the negative log of the hydroxide concentration. So pKa is equal to minus the log, or the negative log, of Ka. When we have a smaller pKa, we have a stronger acid, because the Ka is bigger because it's the negative log. They're inversely proportional. When we have a bigger pKa, it's a weaker acid because we have a smaller Ka. So this is the kind of question you might be asked to sort out on multiple choice on the next test. The pKa of hypoiodous acid is 10.6. The pKa of hypobromous acid is 8.64. Which is the weaker acid? Well, the bigger pKa is the weaker acid, so hypoiodous acid would be weaker than hypobromous acid. And that fits in with the trends we talked about before. Christopher?
If a bigger, wait, I read it wrong, never mind, I apologize.
It's pKa, not Ka, because a bigger Ka would be a stronger acid because you have more product.
See, she knew what I was thinking.
Okay. Let's look at this one. You tell me. The pKa of hypochlorous acid is 7.52. Hydrocyanic acid is 9.21, which is the stronger acid. Class? Which one? Hydrogen. There's no hydrogen there. The hypochlorous acid. Is your nomenclature escaping you? You could have just said the one with the chlorine, right? Or the one with the carbon. Yeah, the one with the smaller pKa. Because the smaller pKa means that it came from something with a bigger Ka, which means you get more ionization. So you get more H+, so that makes it stronger. So again, that might appear in your future as a multiple choice question. Okay, so let's look at how we write these out and how we lead into doing the math. So this is kind of a rehash of Chapter 15 with a little bit of pH stuff from the early part of Chapter 16 thrown in. Write the equation for the Ka for acetic acid. So we can do this two ways. We can do this the fancy way or the generic way. So acetic acid, HC2H3O2, aqueous, is in equilibrium with a hydrogen ion plus an acetate ion. Now, remember, when we have an equilibrium, it means that the chemistry can go both ways. So the acetic acid is breaking down, and the acetate ion is grabbing this proton and going backwards. And it's doing this at the same rate. And this is a reactant-favored equilibrium. This is different than something like hydrochloric acid. Hydrochloric acid breaks apart completely. We use a one-way arrow. So we have a hydrogen ion and a chloride ion. This chloride ion is the conjugate base of a strong acid. Remember, acid-base conjugate pairs differ by one proton. This chloride ion has one proton less than hydrochloric acid. So this is the conjugate base of a strong acid. It has no interest at all in hooking back up with this hydrogen ion. So it just hangs out and sits there and does nothing in the beaker. So that's the conjugate base of a strong acid. This is the conjugate base of a weak acid. It is interested in hooking back up with that hydrogen ion. So you have some very different chemistry going on with strong and weak, And that's going to be something we'll talk about in the upcoming section. So kind of start thinking about strong and weak and their conjugate bases. And if you don't remember the 7 strong, then print them on flashcards, write them out, do whatever you have to do until you recognize strong acids just by looking at them. Now, the lazy way is to just do this. HA, our generic, is in equilibrium with H plus plus A minus. That's what you'll usually see me do because it's less writing. So now we can write the Ka expression. Ka is equal to the hydrogen ion concentration, it could also be hydronium, times A minus, our generic anion, which in this case is acetate, divided by HA. So now go ahead and just at your seats, you write out the Ka expression for the monohydrogen phosphate ion, which is a weak acid in its own right.